So, hello everyone, good evening to all of you, and a warm welcome to my Astronomy TED Talk. I'm so happy to be able to talk to all of you guys tonight. I spent a long time preparing. If I sound a bit tired, I was actually up observing yesterday, so I had around 5 hours of sleep tonight, so please disregard any yawn going on. Anyway, we are going to talk about one of my favorite subjects because it is the subject of my research and my work as an intern over here at UNC. We're going to talk about some strange stars and what I find most interesting, how we can actually find them. But before we get into the subject matter, I would like to introduce myself in a bit more detail. That's me. You can see me in full Carolina gear. As you can see, I have fully arrived in North Carolina and at UNC, where I'm staying right now. But originally, I am not from here, but from Berlin, Germany, and more specifically, actually, in a small place next to Berlin, where I'm studying, which is right down here. So it's called Potsdam. It's one of the places where a lot of astronomy research was going on over the last 200, 300 years or so, and now I am studying there too. Because of the rich history, we have some pretty nice buildings, but nowadays, all the physicists have been hunted out of these. Only the humanities are able to stay in these nice places around the new palace in Potsdam. We have gotten a new and improved campus, actually, so we are now living in the golden cage in Gorn. It's a building entirely padded with golden metal sheets, which has the added bonus of not letting any phone signal in there, so that's nice. So in search to improve my building situation, I traveled across the Atlantic, way over here, and I got a prettier building now at UNC. This is Phil's fault. Don't go inside though, you don't want to see it. Anyway, that is how it looks, that is who I am. Now, what do I actually do? Now tonight, you guys are going to find out that the stars we see in the sky are actually not as lonely as they might appear. If we look up in the night sky, we might only see single dots that are sprinkled all across the night sky, but actually, many stars that we see are not alone at all. Some are way, way weirder. There's a special class of star that is born in an act of cosmic cannibalism between two different stars that is so violent that some of them get flung right out of our galaxy as hyper runaway stars. And some of these partners are so massive that they even visibly warp their stellar companions. We're going to get into all of this tonight and how we know all of this. But to actually find this out, we have to start at the beginning. Now, astrophysicists like to tell you a lot about their research and how we see all of these different weird things out there. But what always interests me is how we gain the knowledge, how we got to this point that we know all of this about the universe around us. And humanity has been working for quite some time on all of these issues. To really get into it, we actually have to start way in the beginning. And we're going to start with the ancient Greeks. Now, it has to be said that they were not the first people to look at the stars, far from it actually. There were many, many tribal cultures that had very important roles for the stars in their unique cultures across the globe. We had also ancient civilizations like the ancient Egyptians or Sumerians that knew a lot of different stars already in their time. I'm just starting with the Greeks because they had a huge influence on our current knowledge of astronomy. And especially these two guys here. It started with Hipparchus, who in 200 or like 150 before the Common Era decided that he actually wanted to find out what kind of stars there are out there on the firmament. And to do this, he used some basic astronomical tools, but mostly his eyes. They didn't have telescopes back then, to look at the sky and to search through the sky. And he wrote down all the stars he found. He wrote down their positions, and he wrote down in which constellations they were, because the Greeks had a vibrant culture. They made up almost all of the constellations we know today. And thus he created the very first, or one of the very first, really big star catalogs, a really important star catalog. Now, unfortunately, his original catalog was lost, but we still have access to the improved version that his, or one of his disciples, or later disciples, Ptolemy, who you see over here, created a bit after his death. So around 150 in the Common Era, Ptolemy actually published his version of the Hipparchus catalog, and that contained a lot of different positions of the stars in the sky. Basically what you can see if you go outside in the dark night. And he didn't only record where he found the stars, but he also recorded how bright the stars were. They had a pretty clever system for that. The brightest stars were called first magnitude stars. They were, so to say, the first place. Those were the way brightest stars. And then they had a couple of different levels in between there, going all the way from the brightest stars you could see with the naked eye down to the way faintest at 6th magnitude. This is the system they came up with. It's not a linear system, so actually the stars that are 2nd magnitude are about, or the stars that are 1st magnitude are about 2.5 times brighter than the stars at 2nd magnitude. The stars at 2nd magnitude are about 2.5 times brighter as the stars at 3rd magnitude, and so on and so on. But it is a very useful system that is actually in about the same form still used today. What is wonderful is that we can actually download and look at the catalog they had back then. This is the Hipparchus star catalog dating back some 2,000 years, plotted by me in a modern computer environment, which I find is amazing. And you can actually see some of the constellations we know, like the Big Dipper over here, or maybe some of you know Cassiopeia, which is the small W in the sky over here, or even Orion. All of these constellations were known way back then. Now this is a pretty impressive feat to map out of the stars, and the brightness is just by eye. And because it is such an impressive feat, this catalog remained relevant for the next 1,500 years. Huge amount of time. It was kept alive by the Persians, who did a bunch of their own astronomy, which is why a bunch of our star names are also in Arabic, like Betelgeuse, for example, which we heard about earlier. They were actually also the first ones to record a galaxy. The Persian astronomer Al-Sufi was the first one to record the Andromeda galaxy, one of the biggest and brightest galaxies you can see in the night sky. And it is this small cluster of black dots right here in this script from about 1064, if I recall correctly, the Common Era. So this was printed a bit after his death, but still amazing that they had all this knowledge back then. Because Hipparchus did such a good job, again, the catalog remained relevant. There was not much need to update it, but even the stars move ever so slightly over the sky, and at some point the catalog became kind of inaccurate, as you would expect, maybe after 1,500 years. So one guy in Europe, Tycho Brahe, took it upon himself to make a new and updated version of the catalog. And Tycho Brahe is a real interesting character. He got his nose chopped off in a duel, actually, but he paid any painter who painted him afterwards to still paint him with his nose intact because he was very self-conscious. And he wanted to do the biggest star catalog since Hipparchus. So he mapped 777 stars on the night sky with pretty high precision. He used modern, or what was modern at this time, instruments to kind of record their azimuth in the sky and all the different parameters like the brightness. He judged that by eye. But he was short about 300 stars, so he did what every good student does, and he just, padded out the length, used ChatGPT, or the equivalent in that era, he just copied it over from Ptolemy. He just copied 300 stars. And then he got to 1,004 stars with a bit more accuracy. Still about the same amount of stars. There was a catalog that was used for some time afterwards, but when we came to the 18th century, or the 19th century actually, there was the need to actually get a bit serious, because science was starting to go, we had industrialization going, and we actually had modern instruments now. We had telescopes. So we could look way, way deeper than we could with the naked eye before. And thus a team in Bonn, city of Bonn in Germany, they took it upon themselves to do a big, big survey. and catalog over 350,000 stars in the so-called Bonner Durchmusterung, it's literally called Bonner survey, all of course in the northern hemisphere. And as you can see, just by recording the positions and brightnesses of these stars down to 10th magnitude now, way fainter than you can see with the naked eye, you're actually already able to see the band of the Milky Way of our galaxy through the sky. And then they expanded it a bit more in the following years by going further and further south too, so they would have a complete map of our night sky after some time. Well, now, that's all good and well, but you might be thinking, okay, what's the use for all of us? We have precise positions and precise brightnesses with these magnitudes of all of the stars in the sky, but they might as well just be bright dots in the sky at this point. We can't really use this information for anything. That's not entirely true, of course. You can use this information to see how the stars move over time, but it is true in the sense that we, of course, at this point didn't really have a physical understanding of how stars work. So how to figure that out? Or in order to figure it out, we needed a bit of a different tool set. We couldn't just stare at the stars and just judge them by their brightness and by where they are in the sky, but we needed to actually do something with the information that is reaching us. And the starlight carries way more information than is apparent by the naked eye. So how can we do that? Well, how do we know more about them? Science was kind of picking up in the 19th century, and we figured out, hey, if I hold this weirdly shaped piece of glass called a prism into a ray of sunlight, I suddenly get a rainbow. Okay? And if I look really close at the rainbow, a guy called Fraunhofer in 1815, he figured out, hey, it's a bunch of weird lines in here that are missing from the rainbow. Okay, that's weird. And also, why are all these stars different colors? If I look really closely, I can see that this star's red, this star's blue. What's going on here? Well, this is where we actually have to get a bit into physics, which I like, but I know might be some trouble to others, respectfully. So we can just go over it from the basics. If we take white light, like the light from the sun, and we use this music record here, we can actually see that the white light is not white at all. It is actually a combination of all different wavelengths of light. Light comes in many, many different colors, which just represent different energies in a spectrum that for a visible range ranges from the very red to the very purple. Now, if we do this for any object that is glowing, we will get a pretty, how should I say this? If we would do this for an ideal object that is just at some temperature, we would get a pretty smooth spectrum out of it, pretty smooth rainbow shape. And I can show this to you right here. We will start at about 1,390 Fahrenheit and go up all the way to 17,000 Fahrenheit. I'm going to show you how the spectrum of this object changes over time. You can see, as I heat an object up, and I figured this out too in the 19th century, hey, when I heat something up, it changes its color. It starts off red, then it becomes white. Let me show it again. Oop. We're getting ahead of ourselves. It starts off red, becomes white, and then in the end it starts getting kind of a bluish tint. And this is what's called a black body spectrum. It's just the radiation that any body that we heat up to a certain temperature emits. So that's why when you have a blacksmith who is smithing some tools or something and heats up to a certain temperature, you're going to see the tools glow. And you're going to see them glow red, and then you're going to see them glow white. And if he's really working hard, you might even see them glow blue, although that's way harder to achieve. However, this black body spectrum isn't enough to really help us in observing the stars, at least not yet. There's something else important that happens when we actually look at stars, an effect that we can use to find out more about them from Earth, and that is what happens in the stellar atmosphere. So in a star we have a stellar core that does fusion, so we fuse light elements to heavy elements that generates a lot of energy, and it heats up the outer layers of the star, heats up the stellar atmosphere to some temperature, at which point it will become a black body and it will start glowing. Okay. The problem now is that this stellar atmosphere isn't perfect. It's actually made up of different atoms. And atoms have this annoying attribute of carrying electrons around them that like to catch light. Actually, if a light ray hits an atom, it may shoot up an electron from a low energy level that's tightly bound to the atom into a higher one. The light needs a certain energy to do this, and this energy will then be missing from the light that we observe. It will become such an absorption line. Now, the opposite thing can also happen, like in a lift, where the electron can actually fall down to a lower level while emitting some light, in which case we will see an emission line, like we got in the trivia questions before, but this case is not so important for us. So this is why spectra of a star, like our sun, have these weird lines in them. It's actually just the light of the star that is generated in the core, or the core that is heating up the star, generating the light, hitting the atoms in the stellar atmosphere, or rather the electrons around those atoms, and causing absorption to happen, causing these electrons to jump around in the energy levels. That's why we're missing the light in the end. Some guy in 1860 also figured this out. His name was Angelo Secchi. And he saw these different lines too, and he also figured out that if we actually don't only look at the sun, but look with this prism at different stars in the sky, the spectra look different for each of them. We see different lines that are missing if we look at different stars. So what's going on here? We don't know yet, but he just ordered them for now by the strength of this line here, which is a line of hydrogen, of the hydrogen atom that we know today, and just ordered them into 3 classes. He just named them 1, 2, 3. He also had 2 other classes, but they're not so important for us, and he called it a day. He was like, okay, these stars, they look weird, we don't really know why, but I'm going to classify them for now, and maybe we can figure it out later. Well, unfortunately he died in 1878, but another guy came along, Edward Pickering, and he was like, hey, what you did is pretty cool, but actually let me redo the whole thing. And he figured out a system that's way more complicated, not only using 3 letters, but using all the letters of the alphabet from A to O. He also found that there are some stars that look like this, where there's hardly any lines at all. This is weird too. Okay. Quick bit of historical information, by the way. It wasn't him at all who figured it out. It actually was his assistant, Wilhelmina Fleming. He put his name on paper though, but she actually observed 10,000 of the 10,300 stars that were in his paper. Kind of a bitch move if you ask me. Oh well. We're going to credit the real author here. Anyway, so they figured out way more classes. They observed a whole bunch of spectra. They made a whole catalog. They called it the Henry Draper catalog of 10,000 stars. And they put them in all these different level classes. But they still couldn't figure out what was going on. Until we came a bit further along and we actually figured out on Earth that if we heat up certain gases, they will actually light up in different lines. What I showed you earlier, these emission lines. And now we could figure out what elements were actually causing these different lines in the stellar spectra. And we knew a bit more information, and actually, we also figured out that this whole black body thing that I showed you earlier, and kind of figured out a bit more how hot these stars are, at least roughly. And this was used by a Harvard student called Amy Jumpcannon to actually correctly sort these stars now by temperature, not by the strength of this line. As you can see, up here, the temperature is very high and gets lower and lower and lower as we go down. And actually for these very hot stars, this hydrogen line is also missing. So because Edward Pickering and Wilhelmina Fleming misordered these spectra at first, when they gave them their nice and easy ABCDEFG system, we are now stuck with a way worse system that goes OBAFGKM, which is the bane of the existence of every astrophysics student learning stars and stellar evolution. Anyway, we now correctly ordered these spectra. And it's very useful because now we don't have to really do much to figure out the temperature of a star. We just have to observe it through a prism, look which lines are there and which lines aren't there, and then we have a rough estimate of the temperature of the star. That's super useful. Now we don't only know the position of the star in the sky and its brightness, but we also know its temperature. And if you plot this with the other information, now it looks way better already, what we have here. So this is on knowledge level 1924, and even a bit before that. And with that, we can now do a pretty fun thing to actually figure out what's going on with these stars. So we figured out by now also that these stars are hot balls of plasma. And since we now know the temperatures and we kind of know the luminosities, if we do some black magic to figure out how far away they are too, we can put them in such a diagram called a Hertzsprung-Russell diagram by the two guys who independently of each other found this diagram. And this is very useful. Now, again, we have the luminosity of the stars up here. Higher means brighter, lower means less bright. And up here, very small, you guys can probably not see it, are the spectral classes B, A, F, G, K, and L. And just by ordering these stars in such a diagram, where we have the luminosity and the spectral classes, we can see a pattern emerge. The pattern is always what makes us physicists happy, because if we have a pattern, we may even be able to figure out what the underlying physical law is that causes this pattern. What can we see here? Well, we can see a main sequence of stars. It's a big band. If you remember from the trivia, our sun is a main sequence star. It is about roughly here in the Hertzsprung-Russell diagram. And those are basically your run-of-the-mill normal star. They start at very big, very bright hypergiants that are blue in color, and then they go down and down and down and down into redder and redder stars until they are at the way lower end down here, red dwarf stars. Okay. How do these stars arrive on this main sequence? Well, that's pretty simple. People later figured out that if you just have a cloud of gas that you compress together, depending on how heavy you make the cloud of gas, how heavy you make the star when it's born, it will land somewhere along this main sequence. Heavier stars go up here, and less heavy stars, lighter stars, they go way down here. Okay? But we see another thing in here, which is called the red giant branch, which are these red and still very luminous, very bright stars over here. And that gave us physicists an idea. Okay, how do these stars keep glowing? Well, it would make sense that they start glowing by a fusion reaction in their core, but that can't last forever because the material will be gone at some point. At some point we run out of fuel, and what happens at the end of the star's life is they will move over from this main sequence all the way up to this red giant branch. That is the explanation, that is how we know, by seeing these patterns in the Hertzsprung-Russell diagram. Okay. So we figured out a bit by now, but even Russell himself said, oh, if only we could plot this diagram not with the 300 stars I have now, but with some thousands of stars. And luckily, today, we're going to do a little time skip now, it's 2024, and we can do that. And we can't only do it with thousands of stars, but actually with billions. Before we get into that though, how can we do that? Well, turns out, if you observe from Earth, you have this pesky thing called an atmosphere, it gets in your way, and it absorbs a whole bunch of light, and you don't really see that much beyond that. But you can solve this problem by just putting your telescope in space. And at some point we figured out how to do that, and we first built the Hipparcos satellite. Nice little callback at this point, by the way. The catalog of stars that this satellite produced was called the Tycho catalog, after the other guy we saw earlier. And later we got the Gaia satellite. And these satellites, with a bunch of complicated modern techniques that I won't be getting into here in detail, they figured out the positions of not 100,000, not a million, or not 10 million stars in detail, as well as their colors, but of roughly 1 billion stars. Let me just show this first. this is how our map looks now. And now we can do way cooler things, because now we can redo this plot. Sorry, I'm skipping ahead of it here. Can redo this plot again. This is the same plot that Herschel Russell did in 1914, but now we don't only use 300 stars, but now we actually have billions of stars on it. And we can see some familiar things here. So even in 1914, we could see this main sequence and this red giant branch. But now we see another important thing. We see this little thing down here, which are stars that are pretty blue or pretty white, but not very bright. And those stars are called white dwarf stars. Turns out they are the dead bodies of the stars that came before us, that have burned out all of their material and exploded in a supernova explosion. After they do that, they move way, way down here and become these stellar dead bodies called white dwarfs that just fizzle out until their energy is gone. Okay, these are the so-called, or these are what I would call normal stars, pretty normal stars. Now some people in the audience might agree with me on some of those stars, but these are your pretty run-of-the-mill stars. The keen-eyed among you might see something else in this Herschel-Russell diagram, though, that is a bit out of the ordinary. Another structure. So we see main sequence of the giant branch and this white dwarf thing over here. But if you look closely, you see there's actually another clump of stars right here. It's not that many, right up here, but they are there, and that's not a coincidence. And these stars are what I'm going to talk about for the rest of this talk. These are called hot subdwarf stars. Weird name, astronomers aren't very good with names. Now these stars can't get here by any normal means. We know how normal stars evolve. They start somewhere here along this branch, then they go up here, then they explode, and then they go way down here. There's no way in this process to get over here though, normally. So this is what makes them strange. How do they get there? And we actually didn't know for quite a while. This is a pretty young field in astronomy. We only figured out that they were there about, I don't want to lie, maybe 30 to 40 years ago. And we only have had theories, good theories, about how they got there for about 20 years now. First off, what are they? Well, we know now that they have about 40% of the mass and 20% of the radius of our sun. Over here is the sun, over here is a hot subdwarf star. At least in average. Of course, there's slight variations between each of the stars, but they are way, way hotter. They have about 4 to 20 times the temperature of the sun, going up to hundreds of thousands of degrees, and they are up to 6 times brighter despite their small size. So we can still pretty easily see most of them from Earth. There's another thing, though, that we are seeing. If we look at the spectra of these stars, the lines move. This happens because of an effect that some of you might know. It's called the Doppler effect. If something is moving towards you or away from you, the light or other waves that this object might emit get a bit squished or stretched depending on the movement of the object. And that allows us to see movement in these objects, and we see that many, many of these hot subdwarf stars move over time. That only can have one explanation. These stars are not alone, at least most of them aren't, but they are in binary systems, meaning that they travel together with another partner. We also only know a bunch of them for now, only 6,616, so it was kind of hard to figure out how this happened. But luckily we have modern computer simulations nowadays, so we have a pretty good idea on what could have happened in the history of these things. How do you get a star to be in a binary system? Well, it might have formed with another partner already from the same gas cloud. Now, what happens for these partners over their life is that they will do the normal stellar evolution individually. Both of the partners will be born, they will be main sequence stars, but then at some point, one of the partners might swell up at the end of its life and travel to that red giant branch we saw earlier. Now when that happens to one of the stars in this binary that were born from the same gas cloud, we can have something that is called a Roche-Low overflow, which means that the star blows up so much that it can't hold its outer layers of gas anymore. What happens to these outer layers of gas? Well, they fall, and they fall on the binary partner. They fall to the other star. The other star literally eats the material from the surface of the bigger star. And this can happen for a long, long time until the outer layers of the red giant star are gone, and we only have the remaining core of the star left. That's when the binary partner has eaten up all of the material. And this core that's left is then the hot subdwarf star. Now the binary partner then might go along its normal evolution, and there might be some other things that are happening later. We're going to get into that. But we can also have another thing happen. Both of the stars are reasonably close and pretty similar in their progression, their evolutionary progression. They might even be close enough to not only have one of the stars blow up and share its mass with the other one, but both of them live in the same common envelope for quite some time, until at some point the stars get so close together that they get so fast that they just eject all of this common envelope into space, because it is too far away and the stars, the cores inside, are going so fast, and that is when we get a hot subdwarf in a very close binary. Weird how that happens. Anyway, now we are left with these close binary stars. One of them, this one in this case, is a hot subdwarf star. The other one is just a normal main sequence star. Now what will happen after a couple of billion more years is that this main sequence star will just become a red giant, like it would normally do if it was alone, and blow up in a supernova explosion. Now, to understand this, you must know that in the system, there's a lot of energy contained in this. Right? We have two massive objects that are orbiting very, very close together due to this whole evolutionary past. It is about, and I did the math on this, 100 billion times the strength or the energy somebody uses in an Olympic hammer throw. 100 billion times. So if this bigger star then explodes with all of this energy stored in the system, the hot subdwarf gets launched right out of the system with all of this energy. And this is what we then call a hyper runaway star. These are the very, very fast stars they are catching, going many, many times the speed of a bullet. Some going as fast as 1,000 kilometers a second, that's the fastest ones, which will get you around the Earth in about 40 seconds. This is how fast they are going. And we can actually see this. I did a nice little simulation here of all of these hyper runaway stars we found, and some other stars. So the red dots are hypervelocity stars, and the white dots are just normal hot subdwarfs. The normal stars, they will continue on in the Milky Way. They will stay bound to the galaxy, but the hyper runaway stars will do something else. You can see it right here. This is simulating from now up until 50 billion years in the future. And you can see all of these red dots are leaving our galaxy. Crazy amounts of power that go into the sea. They can do a bunch more different things. They can get warped by a partner when it's so close that it doesn't cause the envelope to go over, but it causes some warping of the surface where they are not perfectly round anymore, but they're more egg-shaped or ellipsoidal. They can also be so bright that they light up their partner, meaning that if the partner is very close, we actually see that one of the sides of the partner gets illuminated by the hot subdwarf, or they can even eclipse the other star as viewed from Earth. Now, how do we know all of this? Is the last model of technology I want to show you nowadays. Now, other than the astronomers of the olden times that had to count stars by hands, do the Bonner durch Messung, count 350,000 stars by hand on the sky, we have many, many different modern instruments. And one of those modern instruments is the TESS telescope, this thing right here, it was designed to find exoplanets, and this design to find exoplanets allows it to look into one specific direction for around 30 days at a time and take pictures. And it takes pictures every 20 seconds of different stars in the sky. So how can we actually catch these hot subdwarfs in the act doing all of these different weird stars, this different weird stuff? Well, we take so many pictures of them that we just catch them during one of these eclipses happening. And I just wanted to show you at the end of my talk, I just wanted to show you some of the actual data. This is what we look at all day. Look at these different curves. And this is how we are able to tell you all of this. We can see them moving in front of each other and dimming down for some time. Or we can see the reflections happening in the binary partner, or maybe even the warping of the star itself by the partner it's moving with. All with the help of these modern tools, with these modern telescopes. This is how far we've come, from way back in the day, from 150 before the common era, to now 2024. And this is all research that has only been happening for around a couple of decades. So we are not done at all. There's so much stuff that we haven't found yet. And that's why I burn for this, that's why it's my passion. That's why I'm going to keep on researching it until we find out more and more weird stuff about these objects. I thank you all for listening to me go on about this for half an hour today. And thank you all for coming, and see you around next time. Thanks.